Environmental engineering science is a multidisciplinary field of engineering science that combines the biological, chemical, and physical sciences with the field of engineering. This major traditionally requires the student to take basic engineering classes in fields such as thermodynamics, advanced math, computer modeling and simulation, and technical classes in subjects such as statics, mechanics, hydrology, and fluid dynamics. As the student progresses, the upper division elective classes define a specific field of study for the student with a choice in a range of science, technology, and engineering-related classes. As a recently created program, environmental engineering science has not yet been incorporated into the terminology found among environmentally focused professionals. In the few engineering colleges that offer this major, the curriculum shares more classes in common with environmental engineering than it does with environmental science. Typically, these students follow a similar course curriculum with environmental engineers until their fields diverge during the last year of college. The majority of the environmental engineering students must take classes designed to connect their knowledge of the environment to modern building materials and construction methods. This is meant to direct the environmental engineer into a field where they will more than likely assist in building treatment facilities, preparing environmental impact assessments, or helping to mitigate air pollution from specific point sources. Thank you for watching. For more educational videos, please subscribe to WizScience on YouTube or visit wizscience.com.
Civil engineering is everything that you see around you in the built environment, the roads that you drive on, it's the buildings that you go into. Civil engineers are involved in the design and implementation or construction of all of these building elements that we see on a day-to-day basis.
In our new Bachelor of Engineering with honors, the students can choose from a wide range of majors and minor specializations to create their unique skill sets and also gain knowledge for their dream job.
At Griffith, we're reimagining civil engineering for the 21st century. We need to make sure that we're not only taking care of human beings, but we're taking care of the planet at the same time.
Environmental engineering is focused on applications and problem solving, just like every other engineering discipline. But environmental engineering is underpinned by environmental processes. So it was founded with the intention to solve some of our biggest problems globally.
People don't realise how diverse the actual career opportunities are within the field of civil engineering. One of the major areas is working in an engineering design company where you will be designing buildings, bridges, roads, anything that you see around you in the built environment, you can actually construct and project manage those particular projects. Our program is really a hands-on program, either in the classroom or later on in the program they get to actually work with industry collaborators out in the field.
We have a special program called the Industry Affiliates Program, which actually students spend a whole trimester out in industry, and that's actually a transformative experience.
Civil engineering today is such an exciting area, with 7.5 billion people living on this planet and attempting to access really good transportation, really good living environments. The areas that a civil engineer can work in is extraordinary.
Ecological engineering is an emerging study of integrating ecology and engineering, concerned with the design, monitoring, and construction of ecosystems. According to Mitch, 1996, the design of sustainable ecosystems intends to integrate human society with its natural environment for the benefit of both. Ecological engineering emerged as a new idea in the early 1960s, but its definition has taken several decades to refine. Its implementation is still undergoing adjustment, and its broader recognition as a new paradigm is relatively recent. Ecological engineering was introduced by Howard Odum and others as utilizing natural energy sources as the predominant input to manipulate and control environmental systems. Mitch and Jorgensen wrote that ecological engineering is designing societal services such that they benefit society and nature, and later noted the design should be systems-based, sustainable, and integrate society with its natural environment. Odom emphasized that self-organizational properties were a central feature to ecological engineering. Mitch and Jorgensen were the first to define ecological engineering and provide ecological engineering principles. Later they refined the definition and increased the number of principles. They defined and characterized ecological engineering in a 1989 book and clarified it further in their 2004 book, See Literature. They suggest the goal of ecological engineering is the restoration of ecosystems that have been substantially disturbed by human activities such as environmental pollution or land disturbance, and the development of new sustainable ecosystems that have both human and ecological values. They summarized the 5 concepts key to ecological engineering as 1. It is based on the self-designing capacity of ecosystems. 2. It can be a field test of ecological theory. 3. It relies on integrated system approaches. 4. It conserves non-renewable energy. And 5. It supports biological conservation. Bergen et al. Defined ecological engineering as 1. Utilizing ecological science and theory. 2. Applying to all types of ecosystems. 3. Adapting engineering design methods. And 4. Acknowledging a guiding value system. Barrett, 1999, offers a more literal definition of the term, the design, construction, operation and management, that is, engineering, of landscape/aquatic structures and associated plant and animal communities, that is, ecosystems, to benefit humanity and, often, nature. Barrett continues, other terms with equivalent or similar meanings include ecotechnology and 2 terms most often used in the erosion control field, soil bioengineering and biotechnical engineering. However, eco-engineering should not be confused with biotechnology when describing genetic engineering at the cellular level, or bioengineering meaning construction of artificial body parts. This engineering discipline combines basic and applied science from engineering, ecology, economics, and natural sciences for the restoration and construction of aquatic and terrestrial ecosystems. The field of ecological engineering is increasing in breadth and depth as more opportunities to design and use ecosystems as interfaces between technology and environment are explored. Implementation of ecological engineering has focused on the creation or restoration of ecosystems, from degraded wetlands to multi-cell tubs and greenhouses that integrate microbial, fish, and plant services to process human wastewater into products such as fertilizers, flowers, and drinking water. Potential applications of ecological engineering in cities have included the field of landscape architecture, urban planning, and urban horticulture, which can be synthesized into urban stormwater management. Potential applications of ecological engineering in rural landscapes have included wetland treatment and community reforestation through traditional ecological knowledge. Recent lifestyle and habitat planning examples include the permaculture movement.
My name is Renske Terwischa van Scheltinga. I am a PhD student. I was born in the Netherlands. We are in the Hydraulic Engineering Laboratory of the University of Auckland, where we just recorded a video of my flume experiment. This is one of the top places to do research around the world because of its facilities and because of the big variety of people that work and study here. In New Zealand, you still have natural rivers, so it's a really great place to study rivers. This lab has about 10 different flumes, really large ones, and also a lot of smaller ones. So we have a basin of water downstream with pumps. We move the water and the sediment upstream, and then we recirculate it. And because the walls are glass, we can study it from the side and from the top. So we are able to create any feature we find in nature. So a tsunami, a river flood. We can study the transport of really big rocks and also of small particles. The rocks, pebbles, the gravels. There are actually a lot of names for different sizes of stones. So if we're gonna expect with climate change flooding to be more common and to have bigger floods, we need to adjust. We can't stop floods from happening, but if we understand them better, we can limit the consequences.